Okay, everybody, it's time for discussion C-3, solar energy and climate change. All right, so photosynthesis and conjugation. Visible light can be absorbed by molecules that have what's known as a conjugated structure. Conjugation just means you have a large system of alternating single and double bonds. So if we look in beta carotene here, you see you have quite a lot of alternating single and double bonds, and we have some in retinol as well. Now, retinol is actually known as vitamin A, just in case you didn't know. All right, so the amount of conjugation that you have in a molecule will affect the maximum wavelength of light that can be absorbed. The more conjugation you have, the longer maximum wavelength of light can be absorbed. All right, so beta carotene has a much greater amount of conjugation than does retinol, so it can absorb longer wavelengths of light. All right, so the net equation for photosynthesis is here. Now, this is something that you should probably already know. Plants take in carbon dioxide and water. The reaction is catalyzed by light from the sun or ultraviolet. And we're going to produce glucose and oxygen. All right, so chlorophyll is the pigment in plants that allows this process to happen. Now, other pigments, like chlorophyll, can also absorb energy and convert it into chemical energy. So an example of that is purpurine. It's what gives rose madder plants, flowers, their hue, and it is what does the photosynthesis in them. Excuse me, that was kind of rough. All right, so silicon semiconductor photovoltaic cells. Those are actually just solar panels, yo. All right, so a photovoltaic cell is a device made of semiconducting silicon, and it creates electricity when electrons are knocked off from a structure by incoming photons. So light comes in, knocks the electrons off the structure, they become delocalized and can move around. So doping is a process in which certain elements are added to a semiconductor to increase its conductivity. And there's two types of doping, N-type and P-type. All right, so semiconductors created by the addition of group 15 elements, elements like phosphorus and arsenic and antimony, right, are considered N-type semiconductors. And they work by adding additional electrons which can become mobile. That's why it's called N-type, because we're adding additional electrons, and electrons are negative, so it's kind of like negative type. In a P-type semiconductor, the semiconductor is created by the addition of group 13 elements, like gallium or indium. Now that works by creating holes in the structure where electrons can temporarily be held. Essentially, a hole is just an electron deficient structure. And that's why we call this P-type semiconductor positive type, because when we create those holes, we're essentially creating regions of positive charge due to the lack of electrons. All right, so this is a dye-sensitized solar cell, and this is one of the different electrochemical cells we're going to look at in C4, but I'm just going to give you this one here because it's related to solar energy. So what we have on the dye-sensitized solar cell is a pair of conductive glass plates. Inside the conductive glass plates, you have a dye. These red particles here are a dye, and that dye is electron-rich. Now in the middle here, we have titanium dioxide nanoparticles. And then finally down here below, we have a platinum catalyst, and we have an electrolyte consisting of iodide ions and the triiodide ion. All right, so let's talk about the function of this cell. Now, don't forget over here, we have our external circuit. So the first thing that happens is photons will excite electrons which are in the dye. Right? Those electrons are then going to move into the layer of titanium oxide nanoparticles. So this will oxidize the dye and prevent the electrons from returning to it. So then we have our oxidized dye. Now the oxidized dye is going to receive an electron from the solution of iodide ions, thus oxidizing them to triiodide. This will reduce the dye back to its original form. And this is the equation that's happening here. 3 iodide ions makes triiodide, freeing up a couple of electrons to go back into that dye. Then the electron travels through the nanoparticle mesh and will exit at the anode. When it does that, it enters the external circuit and can produce work. Then the electron will return to the DSSC by exiting the cathode, which will reduce the I3 minus, the triiodide, back to iodine. And that's just the reverse of the process we had up here. Right? So this is a battery, basically, that will never die, because each separate step returns the battery to its original form. Now, these are not really good for situations where you need large output, but they certainly could be used to charge your cell phone or something like that. So the advantages: they're inexpensive to operate. Once it's built, it's self-sustaining. The resources needed to make them are plentiful. And the use of the nanoparticle mesh creates a very, very large surface area for the incoming photons, and that makes them highly efficient. Now, for some reason, the IB loves to ask you about this one. So just know those nanoparticles give you a very large surface area. Disadvantages, like I said, they're not great for large-scale applications. And the electrolyte can freeze or expand in cold or hot weather, which makes them poor for extreme climates. Okay, so biofuels. Ethanol can be obtained from the fermentation of glucose. So here we have glucose. It's going to be fermented into ethanol and carbon dioxide, and this is actually the process that is undertaken to create in spirituous beverages. Yeast is used, and the yeast will consume the sugar, produce the alcohol that's in these beverages, as well as the bubbles, the carbon dioxide. So ethanol that is produced in this way can be mixed with gasoline to lower its carbon footprint. We actually talked a little bit about this in C1. Right? So think about how adding ethanol to gasoline will lower the total carbon footprint. All right, so when the plants were alive, they take in carbon dioxide. Okay? So when they are burned, the carbon dioxide that was released had previously been sequestered from the atmosphere. So the carbon that comes out is equal to the carbon that went in. Oh, my phone is ringing here. Let me stop that. I'll call you right back. Okay, so that's a carbon neutral process. All right, so continuing with biodiesel. Biodiesel, is a suitable fuel that is produced from vegetable oils. All right, so the vegetable oils produce a similar amount of energy to regular diesel, but they're very, very viscous, and they gum up the engines of the cars, so it produces additional sludge. Also, they undergo incomplete combustion, which will create more sludge in your engine. All right, so we can get over this problem by lowering the viscosity. And the viscosity is lowered by converting the vegetable oils into smaller esters with a process called Transesterification. And one of two things can happen here. We can just take vegetable oil and react it with methanol in the presence of a hydroxide catalyst and heat to produce methyl esters and an alcohol. Now we can also take a triglyceride, and a triglyceride is just three separate big esters that are all connected into one huge structure of three different chains of ester. So if you react the triglyceride with methanol, you'll also produce methyl esters and glycerol. So let's look at some examples. First one says, deduce the equation for the reaction of pentyl octanoate with methanol in the presence of an alkali catalyst. Just so you know, you're going to want to use condensed structural formulas here because the molecules they're giving you are big. Pentyl octanoate would take up this whole space if I wanted to draw it out. So to do pentyl ethanoate in condensed structural formula, I'm going to start by putting down my functional group. Now if it's pentyl octanoate, I know I'm going to have a chain of carbons in front of the functional group of 5 carbons. So I know that's going to give me 4 CH2s and a CH3 at the end. And if it's octanoate, there's going to be a total of 8 carbons to the left of the functional group. We already have 1 there. So that's going to give me 6 CH2s and a CH3 at the end. And there's my pentyl octanoate. So we are going to react this pentyl octanoate with sodium hydroxide and methanol. Oop. I don't need that 3 there, that's for the triglyceride. And methanol. Now, when we do that, we're going to create a methyl ester. Basically, what's happening, this methyl group on the alcohol is going to attach onto the ester and become the new substituent. And then the hydroxyl group in the alcohol is going to react with the pentyl group that was previously there to make pentanol. So our new ester is going to be methyl octanoate. And the other product formed is going to be pentanol, which will be schmazamo. All right. Now let's look at an example with a triglyceride. So this right here is a triglyceride. You see that it's 3 separate chains of esters all linked together. So I'm going to transesterify this in the same way. Sorry, I forgot about that. So I'm going to add methanol. Well, this time I need 3 moles of methanol because I'm going to need a methyl group for each of those ester chains. I'm going to react it in the presence of sodium hydroxide catalyst, and I'm going to have to heat it a little bit as well. Okay, so if I want to separate this one big molecule into 3 separate molecules, I'm going to have to break those 3 bonds right there. Right? And now the methyl groups from the alcohol are going to join up where I've indicated these lines. And it's going to produce 3 separate esters. So those esters are going to be R prime COOCH3, R double prime COOCH3, R triple prime COOCH3, methyl esters all around. And then this remaining chain is going to react with the 3 hydroxyl groups to produce glycerol. And glycerol is a 3-carbon chain, and it'll have a hydroxyl group on each carbon atom. I'm going to not write the hydrogens out here just because I'm running out of space. So methyl esters plus glycerol. This may seem tough at first, but once you get the hang of it, it's really not that bad. Okay, so advantages and disadvantages of biodiesel. Biodiesel has a high flash point, which means it's less flammable. That means it's less likely to cause knocking in the engine. It has a lower carbon footprint because the ethanol and the vegetable oil all came from plant matter. It's more easily biodegradable, so you're not going to have any Exxon Valdez. It's sulfur-free, so it does not produce any sulfur dioxide emissions. It's sustainable because it comes from plants. And it's a good solvent, which means it cleans out the engine. Now the disadvantages, it is more viscous than diesel, even once you transesterify it. Right? So that still produces some gumming in the engine. Also, it makes it really, really difficult to start in cold weather. So it's slightly lower, has a slightly lower energy content versus petroleum-based diesel. And because it uses a lot of plant resources, it may raise food prices. Excuse me. It's more expensive to produce than biodiesel, or it's more expensive to produce biodiesel versus petroleum-based diesel. We know that diesel can just be siphoned off from the fractionating column, right? So producing it from the crude oil is pretty easy. However, with the biodiesel, you have to grow the plants, take care of the plants, then create the vegetable oil, and then transesterify it. And because it comes from plants, biodiesel contains a lot of nitrogen, so you're still going to have a lot of nitrogen oxide emissions. Finally, climate change. Yep, it's real. If you are a climate change denier, you're going to have to just suck it up for this topic. All right, so greenhouse gases are gases that capture infrared radiation and re-radiate it back to Earth. Remember that infrared radiation we feel as heat. Right, so the primary greenhouse gases are carbon dioxide, water, and methane. You're responsible for knowing all 3 of those, but there are many others. Really, any molecule that has polar bonds in it will have the ability to absorb infrared radiation. Right? So radiation will come in from the sun in the form of high energy UV radiation. Now really there's a whole mix of different wavelengths, but it does come in as UV. That's what gives you a sunburn. Now once the ultraviolet radiation hits the surface, it will bounce back towards space at a lower energy, IR radiation. All right, so that infrared radiation can get trapped by those greenhouse gases and stay in the atmosphere. All right, so the infrared radiation is absorbed by those polar bonds due to bending and stretching. So the bonds actually bend and stretch, and that will cause a shift in the dipole moment between the two atoms that are bonded. Right? So the heat that is emitted is due to the kinetic energy of those bonds, literally because those bonds are vibrating, and vibrating is heat. Right? So it's really important that you know both of these parts, that it's absorbed, the infrared is absorbed because of the bending and stretching, and it causes a shift in the dipole moment. So symmetrical and asymmetrical stretching, if let's say you have a linear molecule, symmetrical stretching would be either stretching this way in the same direction or out that way in the same direction. And asymmetrical stretching would be if one side bends in and the other side bends out. And of course, bending just means these bonds are bending back and forth. All right, so here is a diagram of the greenhouse effect. Again, the radiation comes from the sun as primarily ultraviolet. When it hits the ground, much of that energy is absorbed by the ground, but some of it is re-radiated off, but it's re-radiated off as infrared. All right, so some of that infrared is going to get trapped by the greenhouse gases in the atmosphere. Now, most of it still goes out into space. If it didn't, we'd be like Venus, but most of it still goes out into space, but that little bit that gets trapped is what's causing the climate change. All right, so natural sources of greenhouse gases. Most of the water vapor that's found in the atmosphere is of natural origin. Right? And water vapor makes up 95% of all the greenhouse gases in our atmosphere. Carbon dioxide, even though it has a big impact, still makes up a large portion of the actual climate change. A lot of people do say, well, if it's such a small percentage, how can it affect such a big universe? To which I reply, a virus is millions of times smaller than I am, but it can definitely ruin my week or life. All right, so there's a natural balance between liquid water on the surface and water vapor in the atmosphere, and all has to do with temperature. All right, so when global temperatures are increased, that means that the atmosphere can hold more water. Now, also, gases are, even though we're talking about water, gases are less soluble in warm water or in warm solvents, so that produces more water vapor in the air. And it can create kind of a feedback loop, right? More water in the atmosphere means higher temperatures, which means more water, which means higher temperatures, which could mean adios muchacha. So additionally, don't call me an alarmist just yet, like some people do. A lot of that extra water will also form clouds, and that can reflect radiation back into space, mitigating some of that effect. But water is not really the problem, right? Water, the water cycle is self-regulating. And the carbon cycle used to be self-regulating as well, but now, or at least since the Industrial Revolution, we have been adding additional carbon dioxide into the atmosphere. And it's that additional carbon dioxide which is creating the problem. Right, so we have seen an increase in global temperature since 1880. It's been measured by NOAA in conjunction with NASA and GISS, and it is real. This is an actual temperature anomaly. Now, we're not showing here huge increases in temperature over that time, but it does not take a very large increase in global temperature to make big changes, in our climate. Okay, sources of greenhouse gases. So burning coal, oil, and gas for transportation and energy produces about half of all man-made or anthropogenic greenhouse gases. Industry releases a lot of carbon dioxide, but also nitrogen oxides and CFCs. and that makes up 25% of human-caused gases. And agriculture and deforestation make up the rest. So agriculture causes the emission of greenhouse gases from the flatulence of livestock, as well as the decomposition of bodies. I know that sounds gross, but it is what it is. And also deforestation because of the reduction in the number of CO2 absorbing trees. All right, so ocean acidification. So there are several natural and synthetic carbon sinks on Earth, and carbon sinks are just systems that absorb greenhouse gases. So the ocean is one such carbon sink, and it will absorb around 30% of all the carbon dioxide that is emitted in industry. So if you think about 30 billion tons a year of gross carbon dioxide emissions, give or take, that means that the oceans are absorbing about 10 billion tons of carbon dioxide per year. All right, so when you dissolve carbon dioxide in water, that will produce carbonic acid according to the following equations. So the first one is just carbon dioxide plus water, making carbonic acid, which is H2CO3. The next is carbonic acid reacting with water to produce hydronium and bicarbonate. This is just the dissociation of the weak acid. And finally, the bicarbonate ion can react with water to also produce hydronium and carbonate. Now, this is a natural process. These carbonate ions are what aquatic life forms use for their shells. Right? So increased carbon dioxide can increase the presence of carbonate in the water, but can also increase the presence of acid, which is bad. All right, so if you're asked to back up your assertion that carbon dioxide increases the acidity of the oceans, you can use any one of these equations, but a combination of one or two would be best. Okay, so mitigating measures. So we could do carbon capture and storage like we talked about in C1. Right? I don't know why that says C2, but C1. We could do underground coal liquefaction and gasification, and there's other ways you can capture carbon. We can use scrubbers to remove sulfur dioxide and other greenhouse gases from emissions. Right? When we do this, again, we talked about this in topic 1, but we're going to react water and limestone together with water and sulfur dioxide, and that will produce gypsum, which is calcium sulfate. Then there's sequestration, where carbon dioxide is converted to carbonate by using silicon. In this case, we have magnesium silicate with carbon dioxide to produce magnesium carbonate and silicon dioxide. And finally, carbon recycling, where they use the carbon dioxide as feedstock for synthetic fuels. So they pump it into greenhouses so they can grow all those plants they need to make their biodiesel. All right, and finally, the consequences. So one main consequence of climate change is melting permafrost. Right? Now, there's plenty of methane trapped in the permafrost at the poles, and when the poles melt, that methane can be released. Now, methane as a greenhouse gas is 30 times more potent than carbon dioxide, but methane has a much shorter atmospheric lifetime, so it doesn't stay up in the air as long as CO2. Melting glaciers, this is obvious, right? That can stress water supplies in desert valleys. Like we saw the recent drought in Southern California, which recently ended. And in addition to that, places like Las Vegas are having really a lot of trouble because their reservoirs are drying up because the source of their water is drying up. All right, so we can get increased atmospheric water, which can give us stronger hurricanes. I think we've seen a lot of evidence of that over the last few years. We're going to have temperature extremes, both high and low. Right, so we can't do the thing where the guy goes into the Senate chamber with a snowball and says that climate change is not real. My God. All right, so you can have record rainfall or drought. Right, that will lead to unstable ground in mountainous regions and rapid depletion of groundwater stores. Now, in California, there was a story on 60 Minutes a couple years ago about how their aquifers are nearly dry, which could create a serious problem. And finally, there's sea level rise. Now, it's difficult to forecast how much the sea will rise because it's difficult to forecast how much melting will occur in a certain time, right? But one thing I can tell you is that Bangladesh is nearly underwater. as well as Miami Beach. All right, so that is discussion C3. Sorry, I'm a little tired today, so it wasn't the best, but you're going to have to deal. If you have any questions, bring them to class. If you want to argue any of this science, don't. And have a great day.